I'm going to start now. When I start over again, I'm going to ask you a little question. Is climate binary? You might imagine that everything's all cool and fine, and we live in the Shire, and as warming sort of creeps up on us, all of a sudden we cross some kind of bright line, and we're in Mordor, right? This is a binary view of climate. Things are hunky-dory, things are really bad. And you could draw that line and you could say that's 1.5 C or is it 2 C or whatever we decide. And when we talk about holding global warming to 1.5 C or keeping 1.5 alive or what is our allowable emissions budget to remain within 1.5, we don't really mean this oversimplified view of the world, but it's kind of implied. And what I'm going to argue is that no, climate is non-binary. Climate actually has gradation to it, and there's kind of no end to how much worse it can get. You go from bad to worse to worse to worse. And yes, it's important that we have goals. It's important for policy to be able to work within some kind of framework that sets goals. But the real climate is a gradual gradational process, and it doesn't just cross a line where everything was fine before and now it's bad. And it's actually kind of harder to deal with this than it would be if there were a bright line. It kind of sucks for us, psychologically, because it means we have to live and work and build a future in which we and our loved ones and our civilization and our world are going to be okay, even though things can get worse. There's no sort of line that you could say, as long as we're inside this line, everything's cool. So this is actually kind of a challenging thing for us. All right, outline of my talk. I'm going to show you climate modeling on the back of an envelope. I will actually have a photograph of an envelope, and I will show you how climate works on the back of an envelope. Then I will talk about keeping 1.5 alive. I will briefly take you through carbon sinks and why I think, after 30 years of working on this, that they are beginning to overflow. I have already introduced you to the new paradigm, which is TCRE. That's the hardest part, but since we already did it on the board, maybe we can just skip those slides. No, not really. And finally, we'll come back to this idea of living with ambiguity. So, equilibrium climate sensitivity, ECS, really reflects this logarithmic dependence of the heat captured by greenhouse gases as a function of the amount of greenhouse gases. So never mind the equation. Really, all it means is that you get a certain amount of warming per doubling of CO2, not per 100 ppm, not per, gigaton. You get a certain amount of heat per doubling of CO2. So you get the same amount of heating, of warming, let's call it, when you go from, say, 200 to 400, as you get when you go from 400 to 800, or 800 to 1600. Every bit of warming takes more extra CO2 than the bit of warming did before. And that really is just a fundamental property of absorption. I use the example of sunglasses. Like if I put on a pair of sunglasses and it knocks down 20% of the light, the next pair of sunglasses I put on top of that, not that that would be a good idea, would take out fewer photons than the first one because there's less light left to be taken out. It's a law of diminishing returns. And we've known this for 130 years. This is very, very well established. We've done it in laboratories, we've done it outdoors, we've done it on balloons, we've done it on airplanes, we've done it from satellites. We're really sure about this. So, leads us to climate warming, global warming on the back of an envelope. Using this equation, I should have not just dismissed it. That equation right there Log of 2 is a number, right? I can bring it over there, and I bring the 3 over there, and I do something called anti-logs. That's EXP. You guys probably remember this from, like, I don't know, freshman year. So you can solve for what the CO2 has to be to get to a certain delta T. And that's what this is. To limit eventual global warming to delta T, you got to limit CO2 to this number, okay? Plug and chug. You stick in how much warming you're willing to tolerate, and it's going to spit out an amount of CO2 that you're allowed to have. So, for example, doubling CO2, that's 560 ppm, where the pre-industrial was 280, so that's 3 degrees. You want 2.5 degrees, has to be 499. You want 2 degrees, has to be 445. Uh-oh. You guys know what the CO2 is now? You could ask Dr. Google. But to limit warming to 1.5 C, we have to limit CO2 to 396 ppm. Oops. Why do I say oops? Because CO2 is already 417, and so if that's the case, how is 1.5 alive? How can this be, right? We've just heard from COP26 about keeping 1.5 alive. It's too late. We blew through it, right? We blew through it a long time ago. We blew through it a decade ago. So this is a big problem. Turns out the atmospheric CO2 also fits on the back of an envelope. Global CO2 emissions, about 10 billion tons of carbon a year. Ask me after the talk how big of a pile of carbon that is. It's, oh, what the hell, I'll tell you. So carbon, coal is like 100% carbon, not 95% carbon. A ton of coal takes up a certain amount of space. A gigaton of carbon would fill the Washington Mall from the Lincoln Memorial all the way to the Capitol steps, all the way up to the top of the Washington Monument 10 times. That's 1 gigaton. And we dig up 10 times that much every single year and set it on fire. It's amazing. We are industrious little buggers, we are. 25% of that dissolves into the ocean. Another 25% of it turns into biomass on land, which leaves us 5 gigatons of carbon going into the atmosphere. And all you have to do is divide 5 gigatons of CO2, of carbon really, by the mass of the atmosphere and do a little bit of extra little conversion with the molecular weights. And it turns out that that's about 2.5 ppm of CO2 that gets added every year. If we burn 10 gigatons a year, it turns into 2.5 gigatons of CO2. So, how the hell does this stuff go away? Well, 60 years ago, oceanographers decided for us that the reason the land takes up carbon is because carbon is what plants eat for a living. So I think of it as like the Girl Scout cookies theory of dieting. If there are Girl Scout cookies in my house, my biomass increases over time. And that's basically the CO2 fertilization concept in a nutshell, that plants are hungry. And if you give them more CO2, they eat more stuff. And in fact, if you do this in a greenhouse, that's exactly what happens. If you grow rice in a bunch of different controlled environments in a greenhouse, the more CO2 you give them, the bigger the rice plants get. However, that is not sufficient to make the global biomass get bigger and bigger over time. This is a misconception because everything dies. After it grows a lot of extra carbon, you just get a bunch of extra dead carbon. And that stuff rots, decomposes, and turns back to CO2. So it's not good enough to just make more plants, because then all you got is extra, more dead plants. So what you have to do, believe it or not, is have an imbalance between growth and death that is sustained over time. That's a much harder thing to get than more plants. And in fact, when we look at CO2 over time, back before the Industrial Revolution, it wasn't going up or down. To a really good approximation, The CO2 in the atmosphere was dead steady for thousands of years before the Industrial Revolution. There were no sinks. There were no carbon sinks until we started ramping up the CO2. So something weird happened. When we say that there's a carbon sink on land, we are asserting that plants are growing faster than they're dying. And we mean this globally. And it's hard to get your head around this. It's not true in each little place, but it is true of the Earth as a whole. Since we first had good measurements in the 1950s, we can show, really beyond the shadow of a doubt, that the total amount of growth over decades has exceeded the total amount of death and decomposition over those same decades. It's amazing. Now, how is that possible? When you think about tropical deforestation, when you think about land clearing for, Walmarts in suburbia, when you think about plowing the prairies for monoculture crops, how can it possibly be that the total amount of living material, well, living and dead material in the world is increasing over time? Sort of a shocker. And it absolutely was a shocker. The people in my community, pretty much it was my mentors. It was right about the time I started grad school that this was finally accepted. And the people who taught me about this stuff flat out didn't believe it. They were like, what are you smoking? There's no way. With all this biomass destruction, it's just not conceivable that that the amount of biomass in the world is increasing over time. This is a shocking thing. Well, it is conceivable. Imagine, this goes back to 1850, imagine that growth of plants follows the CO2 curve. So you have extra growth over time, and that implies that you have extra decomposition, of course, because there's more and more and more dead stuff to decompose. But the dead stuff decomposes later than you make it, right? There's a delay, a turnover time between photosynthesis and decomposition, which is essentially the lifetime of plant material, right? It's a little more complicated than that, but it's on the order of about 20 years. Giant sequoias, it's 1,000 years. Blades of grass in my backyard, it's like 2 weeks. But the average over the biosphere is a decade or two. And because there's this delay in any given year, there's more growth than there is death, and that's what CO2 fertilization is all about. This is kind of the concept in a nutshell of CO2 fertilization. We can check. We can actually go around outdoors and fumigate forests with free air carbon enrichment experiments. This is like rings of blowers with CO2 being blown in there, and there's a sensor in the center of the ring that tries to hold the CO2 at a particular constant value. And of course, it's hard because outdoors, and you do it for years and years at a time, and if the wind is coming from this way, you got to blow more CO2 out of this side, and if it's blowing harder, you got to blow even more CO2, and if the wind switches, you got to blow it out of that side. If it's turbulent, it's different than when it's still. All kinds of hard stuff to do. But we have on the order of 100 of these experiments now to work with, and most of them show something like this, that you get a bump of growth in the elevated CO2 ring compared to the ambient CO2 ring, and it goes away after a while. The extra growth only lasts for a few years, and then if you want to get the growth back, you have to give them extra nitrogen. And the reason is because there's stoichiometry going on, right? To build all that extra biomass, especially extra leafy biomass, you got to have extra nitrogen to make more chlorophyll and more rubisco and all this kind of stuff. So it's not enough to give them extra CO2. You got to give them extra nitrogen as well. Well, it turns out we're doing that too. We're fertilizing the crap out of the world. Back in the day, 100 years ago, there was only so much mineral nitrogen to go around. It'd be nice if everything could use atmospheric nitrogen. It's 80% of the air, but it's triple bound N2, and organisms are too weak to pull that N2 apart. So something's got to, we call it fixing the nitrogen. Something has to make it reactive. And before people started doing this, it was mostly microbes that did it, that used metabolic energy to break the N2 bond and make mineral nitrogen, reactive nitrogen. But then these other two guys, Haber and Bosch, came along about 100 years ago, and they started using fossil fuel energy to extract nitrogen from the air, and that led to the Green Revolution, and this is where chemical fertilizers come from. So we are now the dominant source of bioavailable nitrogen on the planet, and that stuff also comes from combustion. So we don't just make it by intentional agricultural fertilizer, we also make it by accident when we burn fossil fuels. So the idea is that you're using air as combustion gas in smokestacks and smelters and power plants and your car, all kinds of stuff. This is what Volkswagen got busted for, right? They were tweaking the emissions tests so that the mineral nitrogen, the reactive nitrogen that came out of the tailpipes was underestimated. But it blows downwind and then it gets deposited. Now, perhaps it's just an accident, but perhaps there's some deeper historical thing going on where most of the nitrogen deposition on the world happens to fall on forests, and forests are like 200 to 1 carbon to nitrogen, so every kilogram of nitrogen that you dump on a forest that's nitrogen limited will take up 200 kilograms of carbon. So it takes up quite a lot. This is a huge mechanism, and it co-fertilizes along with the CO2. There's another one which is really cool, especially around here. I grew up in New England. I moved away to Colorado 40 years ago. Now I'm visiting, and I'm like all nostalgic about the hardwood forest. And it's funny, when you walk around out there in the woods, there's these stone walls out in the woods. What the hell? Why does somebody put a stone wall out in the middle of the forest? Well, it didn't used to be a forest, right? All those stone walls that you find out in the woods they used to be on farms. And people would pick up the rocks and put them at the edge of the pasture or the edge of the field, and maybe they'd use them as boundaries or whatever. But essentially, all those people that farmed that land lost the farm as the economy changed, and they moved into town and they got jobs at retail or offices or whatever, and those trees have grown back. And all of the molecules of wood in the forests of Connecticut used to be molecules of CO2 in the air, so this is actually also a very large uptake, net change of CO2 in the air to rebuild those forests. Now, of course, we put the CO2 in the air in the first place by cutting those trees, and now it's growing back. But there's a delay there. A last landscape I want to quickly talk about is boreal warming. Okay, so here, somebody, well, no, it's too far. Can we get my globe back? I knew there was a reason why I brought this thing, besides just entertaining you guys when the projector wouldn't work. Way the hell up here, up north, it's warming 3 times faster than it is globally. The average warming north of 60 North is about 3 times the average warming rate of the whole world. And part of what the response of ecosystems to that is that the growing season is much longer. There's a lot of hectares of land in that part of the world where there's 50% more frost-free days in the summer than there used to be, even just a generation or two ago. It's amazing. Really large changes. And there's all kinds of knock-on effects. But you can think of it as trees invading the tundra. This is sort of the cartoony version of what's going on up there. And this is a map of 40 years worth of satellite data showing increases in greenness, essentially, increases in the chlorophyll content of the far north. So this is taking up some carbon as well. So we got 4 things. We got CO2 fertilization, nitrogen fertilization, regrowing forests, and boreal warming, all contributing to this net uptake of carbon on the land. How about the oceans? The oceans, quick. Is there more land or ocean? Okay. Jennifer and I went on semester at sea right at the beginning of COVID. Oh my God, what an incredible experience. The very first thing we did, teaching on a ship, 600 undergrads on a ship. We sailed out of San Diego on New Year's Day, and we sailed all the way across the Pacific at 15 miles an hour. You know how they say it's a small world? They're lying. It's really, really big. But anyway, I have a new appreciation for how big the oceans are. having done that. Of course, there's a whole COVID side to that story, but we're not going to get into that right now. All right, what's really happening with CO2 in the oceans is precisely the same chemistry as beer, or precisely the same chemistry as Pellegrino. Jennifer got tired of buying me Pellegrino, so she bought me one of these soda stream machines for Christmas. You take tap water, and there's a CO2 tank, and you go, and you make like fizzy water, which is great. Goes good with cheese. So CO2 dissolves in water, makes carbonic acid. Carbonic acid is what makes beverages yummy. It's the tartness. It's the sparkle. It feels good on your tongue. Now, we also know that the solubility of CO2 is highly temperature dependent in water. This is why beer goes flat when you leave it out on the kitchen table. And it also means that the ocean up here around Greenland can dissolve about twice as much CO2 out of the atmosphere per liter as the water down here. The solubility is much, much, much more in cold water than it is in warm water. So there's a geographic aspect, which is also a circulation aspect of this. Now, the oceans are dark and the oceans are deep. If you've ever been snorkeling or scuba diving, you know that swimming along at snorkel depth, you see all this beautiful colored fish and corals and stuff. But if you go down, especially if you're scuba diving, you go down like 30 or 40 feet, everything starts to look blue, different shades of blue. You go down 100 feet, that's as deep as you can go with scuba, and it's really dark down there, and it's just very, very dark shades of gray. But that's only 100 feet, and the oceans are 13,000 feet deep. So there's a tremendous abyss down there. It's pitch black dark. It's 95, 96, 97% of the ocean that's incredibly dark and really, really cold. It's Davy Jones' locker. It's this enormous freezer at the bottom of the world. It's vast beyond your imagination. And it's 3 degrees Celsius. Even in, Tahiti or Hawaii or whatever, in the tropical oceans, if you go down a few hundred meters, it's 3 degrees Celsius everywhere. And that water sinks to the bottom and it can't come up. Oceans have layers. The bottom water is sealed off by the warm water at the top, which floats on the cold water and is thermally stratified. You can't make it go down. It's like if I tried to take this thing in a swimming pool and swim it to the bottom, ain't going to happen, right? Warm water floats very strongly, and so that water seals off the water in Davy Jones' locker so that it never touches the air. The only place on Earth that the water from the surface can get to Davy Jones' locker is around Greenland in January or around Antarctica in July. And it gets so cold in those environments that water can actually sink to the bottom of Davy Jones' locker. But it's only about 1/1000th of all the ocean that does that every year, which means it takes 1,000 years to fill up the bottom, fill up the deep ocean with this bitter cold Arctic water, and eventually it displaces the surface water. But basically, that deep water hasn't touched the air since the high Middle Ages. 95% of the ocean is completely physically isolated from the atmosphere, hasn't touched the air since like William the Conqueror. Kind of an incredible thing. Doesn't know we're here yet. Doesn't have anthropogenic chemicals in it. Now, how do we know this? We looked. Underpaid graduate students were forced to go on ships for months at a time and woken up with an alarm every 50 kilometers, every 30 miles. They had to come out on deck and drop these things to the bottom of the ocean. You see all these lines? They're really dots. Every one of those dots is a place that the grad students had to get up and drop this thing to the bottom and bring it back up, and they've got samples of all those different depths at all those different points. So we've sampled the entire 3D volume of the ocean and measured not just the CO2, but lots of different things. And when we look at those measurements, we come up with a cross-sections like this. Here's the Pacific, right? From north to south, that's here. Here's the South Pole, here's the equator, here's the North Pole. There's the Indian Ocean, and there's the Atlantic. And the colors show the amount of anthropogenic CO2 dissolved in the water. You can see that it's entirely trapped at the surface. There's a little teeny bit penetrating at the high latitudes, but it's almost entirely confined to the surface of the ocean. So getting the CO2 to go away is hard. You basically have to get it to sink. And it's the sinking water that is the rate limiting step. This is why the ocean sink is 25% of fossil fuel CO2 and not 100% of fossil fuel CO2. Okay, so where is all the carbon gone? You got fossil fuels putting in the air, and then you got exchange of the ocean and land. In the oceans, we got the solubility thing I just told you about. There's also biology that slowly rains it down there. In the land, we got CO2 fertilization, we got nitrogen fertilization, we got land use change, basically regrowth of forests, and we got a response to the warming of the boreal zone. And if you plot these things out for 60 years, the sources are on the top and the sinks are on the bottom. But basically, there's some deforestation, that's the brown, but the big gray wedge up there is fossil fuel emissions. And it's got to go somewhere, right? And this is the partition year by year for 60 years. The ocean is that first wedge below the zero. The land is the next wedge, and then the atmosphere is the bigger of the wedges. So this is it. So that's sources and sinks. Now let's talk about how it's related to climate. So when people did climate modeling before 2006, what we did was to just prescribe the CO2 concentrations. We told the models year by year how much CO2 there was going to be, and the oceans adjusted, and the water vapor adjusted, and the winds adjusted, all this kind of stuff happened, physics. But the input to the model was CO2. And what this experiment, which is called the Coupled Carbon Cycle Climate Model Intercomparison Project, C4MIP, C4MIP did was to change up the rules and say, no. We're not going to tell you what the CO2 is. We're going to tell you what the fossil fuel emissions are year by year, and you're going to figure out for yourself how much CO2 there is in the air, because you're going to calculate the rate of dissolving CO2 and the rate of ocean mixing and the rate of photosynthesis and the rate of litter fall and the rate of deforestation. All that stuff is going to be part of the model instead of part of the input. And a whole bunch of models did this. And there's land uptake and here's ocean uptake. I can reach this one easier. Here's 1850, here's 2100. Basically, back in the day, there were no sinks. And as the CO2 started to rise, you start taking up carbon in the oceans. Now, some of these models are taking up 10 gigatons of carbon a year by the end of the century, and other ones are only taking up 4. So there's a pretty big spread in the oceans. But Jesus, look at the land. Oh my God. What happened on the land was much more crazy than what happened in the oceans. In the land, you go from having a model in light blue there that takes up 11 gigatons of carbon a year of more photosynthesis and decomposition. And on the other hand, you got this other black one that's losing 6 gigatons of carbon a year, putting it into the land. So this is phenomenal. Not only a factor of 2, but opposite signs, depending on which one. The black one killed off the Amazon. Basically, it got so hot that it dried out the forest and it couldn't continue to survive, and so the trees died, and then the carbon eventually decomposed and went into the air and made a lot of extra CO2. And as a result, when you predict the CO2 in these models, holy moly, 300 ppm differences with the same fossil fuel emissions. Oh my God, this is bad. Right? I told you could do it on the back of an envelope. Maybe not. Right? This is the spread of CO2 in the future due to biogeochemistry, not due to fossil fuel emission differences, all the same fossil fuel emissions. So it's kind of nuts. This was a big wake-up call to the global modeling community, like, oh, whoa, we got to pay attention to this carbon cycle stuff. All right, so I'm going to fast forward. This is TCRE. What we find is that if you take those same models, and instead of using time as the x-axis, if you use total fossil fuel emissions, the sum of all the fossil fuel emissions for all those years since the beginning of the Industrial Revolution, the warming is linear with respect to CO2 emissions. And this was a complete surprise. So then we did it again with CMIP5. This was the IPCC assessment in 2013. We did it again with the models that are just coming out now in AR6, right? This is the 2021-22 IPCC assessment. Here's all the models. Oh my God, here's the cumulative carbon emissions. There's the amount of warming. Now, they don't all fall in the same line. The slope is different, but they're all very close to linear. What's going on here? We can think of TCRE, the Transient Climate Response to Emissions, as, I mean, obviously this is just the definition, the change in temperature divided by the total emissions. But you can decompose that into the change of temperature with respect to the atmospheric CO2, right? That's the thing that's supposed to be logarithmic that I told you about on the back of the envelope. And then that multiplies the amount of CO2 in the atmosphere per unit emissions. That's what we call the atmospheric fraction, or the airborne fraction of emissions. So the amount of CO2 that remains in the air times the sensitivity of climate to CO2. And this thing is observed to be constant for a given model. Why? How? It's just nuts. You can imagine, we talked about this when I didn't have the slides. Non-CO2 greenhouse gases should take you up off the line because you've got warming that's not being caused by CO2, so it should be driving it, super linear. You've got radiative saturation, the fact that it's logarithmic, going the other way. Perhaps there's going to be slow feedbacks like permafrost. Evie was talking about, what about the big, bad, scary feedbacks that might take us off the line? So there's all sorts of things that shouldn't be linear here. We can decompose it a little bit more mathematically. What this says is it's the airborne fraction times the radiative forcing, and the denominator, so sorry, India, it's actually two different terms. There's the feedback factor, never mind how the math behind that, but you can sort of collapse all the feedback into a number, which is lambda. And then there's this other number, kappa, which is how much heat it takes to warm up the ocean, a certain amount. So it's the ocean thermal inertia. And we know from first principles that as emissions accumulate, that radiative forcing number, theta, should decrease. It's logarithmic. It takes a doubling of CO2 to produce the same amount of radiative forcing as the last doubling. As the temperature warms, the sinks are supposed to weaken, and so the airborne fraction should increase. And as the surface ocean warms up, kappa should change. So all three of these things should be changing. They're all very dynamic, especially over a very large emissions range like we've looked at. So the fact that they somehow cancel out and produce a constant value for that thing on the left-hand side, whatever, somebody know what that Greek letter is? What? It's capital lambda. Okay, thank you. Capital lambda should be all over the place, but it's a constant. What? So somehow they cancel over a huge range of CO2 concentrations. In fact, it's not even scenario dependent. So here's the RCPs, right? RCP 2.6. Here's our historical emissions. We're up to about 600 gigatons now. You can follow the RCP 2.6. That's the stabilize at 2 degrees. You can see that it continues to increase until about 2050, and then it stops going up. And in 2100, it's the same total emissions as it is in 2050. That's our good outcome. That's where we obey Paris. But there's RCP 8.5. You can just continue following that same freaking line all the way out there to 2100, where we've emitted 2,500 gigatons of carbon. It's just shocking. It's astounding. It's like, how can this possibly be? But it's a nice, easy number to remember. It's 2 degrees Celsius per 1,000 gigatons of total historical emissions ever. That's your budget, if you will. So that actually makes it really easy to define an allowable emissions budget. You basically, you got your temperature, you got your cumulative emissions, you draw a horizontal line from the temperature where you want warming to stop, and then you follow that line down, and that's the total amount of emissions you can ever emit. And you figure out where you are now. Turns out we've only got about 100 gigatons left to limit warming to 1.5. Uh-oh. We're emitting 10 per year. That means things are running out pretty quick. But because of the sinks, because of the persistence of the sinks in the models, 1.5 is still alive. So based on that TCRE logic that I just showed you, there is a limiting warming to 1.5. Emissions trajectory goes to 0 in 2040. And there is a 2-degree limit at zeroing out emissions in 2060. So this concept appears to show that we're not screwed, which is kind of nice. It also means that warming is going to stop. Warming will stop pretty much at the same time as emissions stop. There's no warming in the pipeline. These are a whole bunch of different models that were run out 50 years past the end of emissions. And what you see on the y-axis is watts per square meter of heat, of radiation. And the ocean is warming all those models. The red things are above zero, means there's heat coming out of the ocean. We should be continuing. This is the warming in the pipeline. But it's offset in all those models by a blue bar, which is the ocean sink, and a gold bar, which is the land sink. And pretty much they all add to zero, right? The little diamonds show the sum of all the forcing 50 years out after emissions stop. Now, should make you a little suspicious that the sink mechanisms are very different in the different models. Like look at just the gold bars across the models. I'd say they vary by at least a factor of 10, right? The land sink is uncertain by a factor of 10. The ocean sink is uncertain by a factor of 3. The ocean heat is uncertain by a factor of 50 or 60%, and yet they all cancel out. Really? What? So this has been tested. There's a new MIP, right? MIP stands for Modeling and Comparison Project. The Zero Emission Commitment MIP, ZEC-MIP. ZEC-MIP allows the warming to continue, and then bang! At time certain, you turn off all the fossil fuels, and you get that blue line. Holy shit, it's just dead constant. Now, if you hold CO2 constant, you continue getting warming. That's the red line. But we're not holding CO2 constant. We're holding emissions to zero. And so the sinks compensate for some of that ocean warming, as we just saw. So this is a photograph that my mother took of me when I was 3. So you're telling me that we can predict future carbon sinks under falling emissions so precisely that we can say they'll exactly cancel changes in ocean heating, in methane, in aerosols, and all these complicated nonlinear things that we used to think were really hard to model. I mean, color me skeptical. I just find this hard to swallow. It's perhaps because I'm old and curmudgeonly, but it's just, I mean, evidently I felt that way when I was 3 as well. So sink saturation. Here's the sink, and see how it's getting saturated? It's filling up. Okay. The land sink is very vulnerable. Maybe you could imagine CO2 fertilization has legs because the CO2 continues to pile up. Maybe not. You're shaking your head. Like, don't say that. Okay. But not nitrogen, right? If you dump a bunch of Miracle-Gro on your tomato plants, they grow more. Duh. But if you dump 10 times more Miracle-Gro on your tomato plants, they will not grow 10 times more, right? There's a limit to how much you can fertilize things, and beyond that limit, it doesn't do you any good, and maybe even does harm. Similar, even maybe worse with boreal warming, right? A little bit of boreal warming, and you got trees in the tundra, but a lot of boreal warming, and you got thawed permafrost, and then you're in a world of hurt. So land sinks are not very safe, in my expert opinion. Land is not a safe place to stash thousands of gigatons of fossil carbon. The ocean may be safer. It's slow. It's got this 1,000-year cycling that's going to take forever to fill up. But it's a little scary on the longer term because there's also ocean acidification, and that's even potentially a worse problem than the problems on land. But it's a longer-term problem. So I have in my head a simple box model where there's the atmosphere, there's the plants, they put carbon in the soils. There's the surface ocean, it puts carbon in the deep ocean. And before there was fossil fuel emissions, these things were all in equilibrium with each other, right? There was a carbon flowing all around, up and down and around, but there was no net accumulation. The difference in CO2, partial pressure between the air and the water and the plants, was zero, and there were no sinks. Along came fossil fuel emissions, and we pumped up the CO2, the PCO2 of the atmosphere, and now there's overpressure. And so this CO2 is penetrating down into the land and into the ocean, and it's accumulating in those reservoirs. But then when we stop burning fossil fuel, we actually imagine that the overpressure will reverse, that you've now got more CO2 stuffed down into those boxes than is in equilibrium with the atmosphere. Or at least you could imagine a scenario in which that were the case. So I have not proven that TCRE is the real story. And I have told you that it makes me uneasy. But really, who cares whether I'm uneasy, right? That's really not a very good metric for whether something can be true. What I'm going to leave you with is ambiguity. What if we're wrong? What if those perfect cancellations among all those different Earth system models doesn't actually come out to be the case? And in fact, come on, let's have a little humility here. For 50 years, we've been watching the CO2 going up, and we've watched the sinks increase and increase and increase. If we're really good, we'll stop that, right? We'll stop making the CO2 go up. But nobody alive has ever seen that happen. No scientist has ever studied a world in which CO2 was not going up, because that world has not existed in our entire lifetimes. We don't have experimental data. We don't have a historical record of falling CO2 to look at to see how sinks react to falling CO2. So it's kind of scary to be in that ambiguity. It seems conceivable to me that the sinks might fight us on the way down just as they helped us on the way up. That half of the CO2 that we put in the atmosphere was removed for us, thank goodness, by the Earth system for free, 50% emissions reduction. And that if we try to draw that CO2 back down, for example, through carbon dioxide reduction technologies, that could actually fight against us on the way back down. I want to point out that there are two words Michael Mann has used about this, and both of the words are important here. He has stressed urgency of this problem. This is like the most urgent problem there is. We got to do something about this. But that also implies agency. Agency means you can do something about it. You have the power. You have agency to affect the outcome of this. And the TCRE concept, if nothing else, provides us with the potential that we could stop global warming. When we stop setting carbon on fire, the world will stop getting hotter. That's the sort of message of TCRE. Finally, I want to talk a little bit about hope. I've borrowed the quotes that I'm about to show you from Dave Roberts, who I guess gave a talk here last year. Somebody told me that. Anyway, Dave Roberts used to write for Vox. Is there hope is the wrong question. It's like, look, if I was here on the stage and I had like a chainsaw, do you have hope that I'm not going to cut my leg off? What a stupid question. You know, don't cut your leg off, right? It's not about, I hope I don't cut my leg off. It's like making a choice. There's agency here. There is no such thing as game over or too late or we're screwed. This is a non-binary climate. There is not a bright line that once we cross it, it's the end of the world. It is certainly not the case that we have only 12 years to act. And in fact, you're going to continue to fight this your whole lives. And your children are going to continue to fight it. And it's going to be something that's always going to be fought. We're not going to stop fighting at 1.51 or 2.01. We're going to keep after this until we're done. The stakes will always be enormous. Time will always be short. There will never be an excuse to stop. One last thing. Any of you ever watch Game of Thrones or read the book? Some of you. There was a character in the book and the movie, Arya Stark. And when the thing started, she was a little girl, and she learned how to sword fight from this guy who was a swordsman of Bravos. And in their culture, they had the old gods and the new gods. And she said, well, do you follow, swordsman, do you follow the old gods or the new gods? And he said to her, there is only one God, the God of death. And what do we say to the God of death? Not today. Thank you. Let's go eat cookies. Oh, no, we should have questions, I guess. Should we have questions or cookies?
Yes, Scott, can I just interject really quick? So we do have cookies in the back. We're all adults. I don't think I need to say this, so please only take one. I know they look really good. There's a box of gluten-free, and there's a box of vegan that are smaller if either of those are your category. We said 7:30, so you're all free to go if you want. You're also free to stay and ask questions. Thank you, Scott.
Thank you. You in the front row.
Oh, I'll be the loud student. So I had not heard this concept before. And you're saying that all these super complicated nonlinear equations that are within every single model always end up with a straight line.
Go figure. Sorry.
And it's not anything that's part of any of the first principles.
We have no reason to expect the linear behavior of TCRE that I am aware of. I mean, I've been reading up on this a lot. So nobody has made an argument from first principles why this should be the case. It is an emergent property that happens in almost every model. They don't give the same slope, but they all produce a linear response. It's amazing. Yeah.
I don't believe it either.
I don't believe it either. That's good. Yes.
To make sure I understand, does TCRE imply that we're never going back, like things will never be cooler than today?
That is a great question, and I think it kind of does imply that. I think what it means is that it gets warmer and warmer and warmer, and then it doesn't get colder. Now, maybe if you let this thing go for another 1,000 years or something like that, when the sinks... so I didn't talk about this, but there's a whole another lecture I could give called The Long Tail, which has to do with what is the fate of CO2 after we're done. And there's basically four places that it goes. It goes into the land, right? We all know about photosynthesis. But that's a very limited reservoir because it comes back out at the same rate that it goes in. So it's hard to get very much of it more to go in the land in the long run. It dissolves into the oceans, and as we've seen, the real rate limiting step is getting it into the deep ocean. So it takes 1,000 years to turn the ocean over once, and at that point you're about 65% of the way towards chemical equilibrium between the fossil fuel in the air and the fossil fuel in the deep ocean. You turn it again, and now you're 90% of the way to equilibrium. You turn it again, and now you're 99% of the way to equilibrium. So that's the year 5000 that we've now chemically equilibrated the atmosphere and the deep ocean. And now the rest of the story depends on how big that total fossil fuel emissions ever is. If we stop soon, that's enough. We're done. You equilibrate it with the deep ocean and you've reached a new equilibrium. But if you emit too much, then the equilibrium is at a much higher concentration in the atmosphere than the pre-industrial concentration. And at that point, I'm sorry, but a terrible thing happens. The terrible thing is that calcium carbonate in the ocean dissolves. Calcium carbonate in the ocean is seashells, it's foraminifera, it's coral reefs, it's a huge part of the marine biota that is related in some way to calcium carbonate hard parts. And those become chemically unstable beyond a certain amount of CO2. And that actually increases the alkalinity of the deep ocean water, and you can take up more carbon from the atmosphere. So that's a sort of 10,000-year process. And then if the fossil fuel emissions is even more than that, then you have to dissolve rocks on land in addition to the calcium carbonate in the oceans. And it's primarily like granite and basalt on land that dissolve, and that's a 100,000-year process. So you know, let's just stop soon, and then we won't have to worry about all that. But you're right. I think just on its face, this bizarre cancellation implies that you warm and you warm and you warm until you stop burning, and then you don't warm anymore, but you don't cool anymore either. Great question. Yeah, Warren.
So I'm wondering whether, and maybe it's too big to answer, that the underlying math of the models accounts for like the tipping points. So like when we did our box model calculation, most of it assumed, circularity to where the carbon went through the model.
A cycle.
Yeah, it was, it was simple, but I'm thinking of like, NASA published a paper about turbidity in the air, in clouds at some point. That hits some kind of ppm threshold, and you no longer have the same rate of cloud formation anymore, and that changes.
So you're saying there are thresholds in the climate system.
Right. So does the math in the underlying models that make up the final CCRD, well, I guess it's a bunch of models.
Yeah.
But are they accounting for like the point at which, like, because this is like our little crucible burden machine and it's circulating, and at some point, like, it changes the equation.
Well, so different models are different, and there are dozens of these models out there in the world. These are full-blown Earth system models, the kind that they run at NCAR, the kind they run at NASA, the kind they run at the Max Planck Institute in Germany. And they will have, some of them will have these nonlinear tipping point kinds of things in them, not necessarily as part of an equation, but as a result of equations. So, I mean, to some degree, yeah, that stuff is in there. This is, I can't really defend this, right? I'm telling you what scientists have found, and I'm telling you, furthermore, that this is not something that just showed up like last year. This is like a decade's worth of work, 2 IPCC cycles worth of assessment. It's been studied a lot. You guys are all like, well, how can that be? And it's exactly what I'm saying. How can this be? But there it is. I'm not sure I answered your question, but I wasn't really sure what your question was, so we're leaving. Yeah. You look like you have a question.
So my question is, you mentioned towards the end about what if the sinks fight back. So in terms of, especially the land sink, like what are the mechanisms that you're...
Of fighting back?
Yes.
Well, so it's really my simple boxes. If you imagine that we get really serious about carbon dioxide reduction, if you imagine that we plant 1 trillion trees and we, well, actually that's a bad example. So suppose that we do biomass energy and carbon capture and sequestration, and we have accelerated chemical weathering. We have all these different mechanisms, and we're trying to suck CO2 out of the air. At that point, the PCO2 of the air will be less than the PCO2 of the surface ocean, and less than the, well, think of it maybe through photosynthesis and respiration. The lack of CO2 in the atmosphere will suppress photosynthesis on the land, but the soil organic matter will have developed under a higher CO2 regime where there was more photosynthesis on the land, and therefore you'll be out of equilibrium precisely the opposite as you were on the way up. So this is, I don't know that this will happen, but it seems reasonable to me. And it is what happens in my box models if I suck CO2 out of that top box. I got one more, actually, better answer for that. It's not about the land. But in 1963, the US and the Soviet Union agreed to stop blowing up nuclear weapons in the air. And they said on date certain in 1964, this treaty is going to go into force and we're no longer going to blow up nuclear weapons. And so what do you think they did between the time they signed and the time it went into effect? There were dozens and dozens of nuclear weapons tests. And it made a huge pulse of radiocarbon CO2, which has been tracked going